All right. Last time I started talking about moments. And the definition of a moment mathematically was the moment about some point A is equal to a row vector crossed with a force vector. This row vector is a vector from the about point to the point of force application. So I want to say a couple things about moments. Okay, let's. So here are a couple of important things to keep in mind about moments. Notice first, a moment is always a vector. And the direction of the vector is along the axis of rotation according to the right-hand rule. Second, because of number one, if you're doing a problem in 2 dimensions, if you're working in the XY plane, moments only have a non-zero Z component. And so later as we go on, I'm going to start out by writing all moments as 3 component vectors. But as we go on, just to save pen strokes, I'm going to start, when we're working in the XY plane, I'm going to start writing moments as just single numbers. But it's important to remember and recognize that that moment is always a vector. And so even if I'm writing it as a number, that number is really a Z component of a vector. Okay, so let me draw a picture of how this works. So if you have a bolt that you're trying to turn with this wrench, and you're trying to turn it by applying a downward force F. To figure out the direction of the moment, you have to think about what direction of rotation that force would cause. You know, in this case, it would produce a counterclockwise rotation. And so then the direction of the moment If you use the right-hand rule, that's supposed to be a hand, you know, with the fingers going in the direction of the rotation of the and the direction of the moment is in the direction of your thumb, so out of the page. So this force would produce a moment out of the page, like that. Any questions about how that right-hand rule works? Yes. This is out and an X like that. So the way it's supposed to look like an arrow either going towards you or away, those are supposed to be like the feathers, you know. So let me do a 3D example. In 2D, there can only be a non-zero Z component. In 3D, you can have 3 non-zero components. So that's what we're going to get in this example. So let's say there's a plate connected to the wall. And there's a hook in the middle of the plate. And a cable connects that hook to a point directly above the corner of the plate. Let's say this length is 2 meters. This length is 2 meters. This height is 1 meter. And let's use a coordinate system with the x-axis this direction, the y-axis up, and the z-axis like this. So now let's define point A right here. That's going to be our about point. And let's say that cable tension is 10,000. 10,000 newtons. What's the moment the cable applies to the plate about that point A? So the first thing we have to do is come up with a representation of that force. And that force vector is going to be equal to the magnitude, 10,000 newtons, times a unit vector pointing in that direction from the center to where the cable's connected. Any questions about that direction? Okay, so now what we have to do is figure out a vector that goes from the center, from the origin to that point up at the top. So how far in the x direction do you have to go to get from the center of the plate to the wall connection? Yeah, let me label this. Let me call this B. So B is equal to, yes, you have to go -1 in the x direction. How far in the y direction? 1 in the positive y direction. And then how far in the z direction? 1 in the positive z direction. And I'll call that my vector u. That's a vector that's in the direction we want because our origin was the starting point. It's just not a unit vector yet, so we need to divide it by its length. If you have a TI-89 or an Inspire, your calculator will create a unit vector out of this. But if you don't, then you got to do it like a sucker. So the length of this vector is -1 squared plus 1 squared plus 1 squared all square root, which is √3. And then the unit vector we want is 1 over √3 times the original vector, -1, 1, 1. And that gives you -0.577, positive 0.577, positive 0.577. So the force vector applied by that cable is 10,000 times this, which is, and actually there's a 3 at the end of these, just for a little more precision. So then you get a force of -5773, and then positive and positive. All right, so now let's fill out the values for rho, F, and the moment about A. The rho vector that we want goes from the about point to the place where the force is applied. So that rho vector, what's its x component? And it's the magnitude is 1, but you have to go from A to here, you have to go 1 in the negative x direction. So the component's -1. What's the y component? 0. And what's the z component? Yep, +1. We just calculated this force vector, -5773, and then positives. Now just take that cross product to get the moment, and you get -5773, 0, -5773. These forces have units of newtons. The rho vector has units of meters, and so this moment, take the cross product, you get units of Newton meters. And so what does that say about the direction of rotation that this force would produce if there was like imaginary hinge here, like this thing would rotate around that point. Well, it says that the axis has a negative x component and a negative z component, so it's going to rotate. That force is going to make it rotate around an axis like that. Any questions about that problem?
So if that were to rotate, it would be just a plane on the x-axis?
It would be rotating about, so let's see, this gets hard to draw. So if there's the body, and you had an imaginary like ball and socket joint there, we figured out that the axis has a component this way and a component this way. So the axis is in the XZ plane, sort of like that. And this force applied here would make this thing rotate according to the right-hand rule this way around that. That drawing is no good. But the idea is that the direction of that moment vector, according to the right-hand rule, gives you the axis that that force would cause a rotation around. Okay, what are moments good for? Oh, before I do that, sorry. Notice one thing here. The moment produced by a force isn't defined until you choose an about point. So in other words, a force doesn't produce a moment. Force only produces a moment about a given about point. You choose a different about point, you get a different moment. Yep. Yeah, so that's the way to think. I mean, it depends which way you're looking at the axis, but yes, it implies you put your thumb in the direction that the vector is going, and your fingers tell you the direction of rotation around the body. So any force you apply, it produces a moment once you choose what about point you want. There's one type of moment, one special kind of moment that is not dependent on the about point. So there's one type of moment that doesn't depend on the choice of about point. Or in other words, no matter what about point you choose, you get the same answer for the moment. And that is the moment of a couple. And so let's think about, well, I have to tell you what a couple is. A couple is a pair of equal and opposite forces acting at a distance from each other, acting some distance apart. So I'm going to go through just a little mathematical calculation to just show that if you have this case where you have two forces acting equal and opposite on a body, then whatever you choose as the about point, that disappears from the calculation. You can eliminate it from the calculation. I guess let's say that this is the body, some random body, and let's say that there's a force vector F acting at a point P1, and an equal and opposite vector, force vector negative F, acting at a point P2. And what I'm going to do is I'm going to choose an about point A. I'm going to calculate the moment produced by each one of these forces. I'm going to add them together to get the total moment produced by this couple. And we're going to see that the A disappears. So let's say this is the about point A. And I'm going to show the dependence on A cancels out when you add up these moments. All right, so the sum of the moments about A is equal to, so the moment produced by F about A plus the moment produced by negative F about A. The moment produced by F is its row vector crossed with the force vector. How would we represent the row vector for this force? What's the definition of that row vector? Yeah, so it's P1 minus A, right? The coordinates of P1 minus A. So we're going to take the quantity P1 minus A and we're going to cross it with F.
What does P1 and the A have vectors? Are those just points?
Points, coordinates are vectors. They're vectors from the origin to the point. And so, yeah, you can always do vector math with coordinates. And now the moment produced by the negative F. What's the row vector for the negative F? P2 minus A, yep. And we're crossing that with negative F. And now we'll use some of the properties of the cross product. This gives us P1 cross F minus A cross F plus P2 cross negative F minus A crossed with negative F. And then we can pull the negatives out for these second two terms. So we get P1 cross F minus A cross F minus P2 cross F plus A cross F. And now you can see that the two terms that have A's in them cancel each other out. You can regroup these and you come up with a final answer that says P1 minus P2 quantity crossed with F. A disappeared. So the moment of a couple is the same for any about point.
Same answer if you switch to
Yeah, that's a good question. So yeah, there's some sort of funny stuff here that you have to kind of make sense out of. Sort of related question, I think, is how did I decide which one of these is F and which one of these is negative F? You know, it seems arbitrary, right? I mean, these are just random vectors. Why couldn't I have called that F and that one negative F? And the answer is you can. You just have to make sure that whatever you're calling F is associated with P1, and whatever you're calling negative F is associated with P2. Okay, in order to use this formula, you can call them whatever you want if you want to go through the derivation each time, you know. But if you want to use that as a formula, you need to always group the F with the P1 and the negative F with the P2. One more thing about this. It's really the moment of a couple. But people usually just call it a couple. Referring to the moment. And when you're putting it in this, like when you're organizing it in a table, where you have a column for row and a column for F and a column for the moment. When you're dealing with a couple, let's say that we have a couple that we're calling MR, like reaction moment. The row vector and the force vector don't have any meaning. They don't tell us anything. And then we just put the MR in here. To think about a couple physically, so like a physical interpretation of a couple. One you could think of like a screw. So to turn this screw, you put a screwdriver in. You can imagine, well, first imagine a screwdriver that's not continuous the whole way. It's just two prongs, okay? And when you turn that screwdriver, one prong is applying a downward force here and the other is applying an upward force there. Equal and opposite forces that have the effect of no net force because they're equal and opposite, but they cause a rotation because it's producing a moment. So for a screwdriver, you're applying a force there and an equal and opposite force there. Well, what about the fact that a screwdriver isn't 2 points? It's really flat, and it's applying forces all the way along. Well, it's applying forces like this. They're all in pairs, equal and opposite pairs. And so there's a continuous set of couples that's causing a rotation without causing a net force. The other, another example is this guy's standing here, minding his own business, and you throw one of those workout balls at his face and another one at his feet, It'd be a hilarious YouTube video. So his center of mass would not accelerate because these are equal and opposite forces, but he's going to rotate this way because you're applying a pure moment causes a rotation. It doesn't work if the person knows it's coming. Okay, so I'm going to do another example. We're almost all the way to being able to do like real body problems. So let's say that there is a circular body. And the loads applied to this body are a couple of negative 450 Newton meters. And a force F2 applied here at an angle of 30 degrees. That was definitely a sneeze. That was easy. Okay, this is a force F1. And this is the about point A. And we want to know what is that force. Oh, this is F2. What's the force vector F1 and the value F2 if this object is in equilibrium? So we're going to use Newton's second law and the moment equation. Newton's second law says the sum of the forces, or the net force, is equal to 0. That gives us two equations in 2D. And the moment equation says the net moment about A is equal to 0. That gives us one useful equation in 2D. The reason that moments only give you one useful equation in 2D is because they all act about an axis parallel to the z-axis. So there's only a useful z component. Okay, so let's, and I need to give dimensions for this thing. Radius is 1. One meter. Okay, so fill out the table, row, F, moment. So one by one, we're going to go through these loads. Force F1, what's the row vector for that force F1? I didn't give directions, but let's use the normal ones. Okay, so to get from A to where this F1 is applied, you have to go in the negative Y 1 meter and in the negative X 1 meter. Row vector we want is this one. So the row vector is going to be -1, -1. And I'm going to write the third component 0 for now, because everything's just happening in the XY plane. And then the force vector here is F1. We'll break it up into X and Y components. So F1X, F1Y, 0. And the cross product is 0, 0, negative F1Y plus F1X. Any questions about that one? And so now we'll go to this force F2. What's the row vector for the force F2? You go in the positive X direction 1, but then you also have to go in the negative Y direction 1. You start from A and go to where the force is applied, yeah. So 1, -1, 0. That force vector is, so if you think of putting the tail of this vector at the origin, the angle from the positive x-axis is 180 minus 30. So cosine and sine of 150. And you get negative 0.866 F2, positive 0.5 F2, 0. And then the cross product says 0, 0, 0.5 F2 minus 0.866 F2. Which I guess I can rewrite as 0, 0, negative 0.366 F2. And then the last one is the couple. We don't care about the row vector or the force. The way that rotation is shown is in the positive z direction. This says that it's negative relative to that requirement. So that's going to be a couple of 0, 0, negative 450. Any questions about that? Now Newton's second law. I'll just use the x and y components of these. And I'm just going to add up the things right down this column and put them here. So F1x, F1y plus negative 0.866 F2 0.5 F2, and that's all the forces equal to 0. And now for the moment equation, I'm going to take all of these vectors and add them up and set them to 0. So we have negative F1y plus F1x minus 0.366 F2 minus 450 is equal to 0. So I'm going to rewrite these. This is a system of 3 equations. The first equation says F1x minus 0.866 F2 is equal to 0. The second one says F1y plus 0.5 F2 is equal to 0. And the third one, I'm going to get the constant on the other side, says F1x minus F1y minus 0.366 F2 is equal to 450. And I'm going to write this as a matrix and solve it with reduced row echelon form. There's equation 1, 2, 3. And the columns represent F1x, F1y, F2, and the constant. The first equation says F1x, we have one of those. F2, we have negative 0.866 of those. The other two are zeros. Equation 2 says F1y's, we have 1. F2's, we have 0.5. And the other two are zeros. And equation 3 says F1x, we have 1. F1y, we have negative 1. F2, we have negative 0.366. And the constant is 450. Remember, you have to move that constant to the other side of the equation, or all your answers are going to be backwards when you do this. And if you run that through reduced row echelon form, you get F1 equal to 389.7 and negative 225. That's in newtons. And the force F2 is equal to 450. Any questions about that? Yeah. The joint applies a couple, or a pure moment. You know, it applies a couple, which means it applies a moment that's independent of what you choose as the about point. Okay, so the first ones, I'm going to sort of go back and forth between the document camera and this. Okay, so the first set of joints, joint category 1, I'll call this. These are joints that apply a single force in a known direction. The first one is contact without friction. So if this is the body you're thinking about and it's in contact with the ground there and you're told that this is frictionless, then a free body diagram, let me call this body 1 and let's call this ground looking thing body 2. So a free body diagram of body 1, not the whole thing, but just a part of the free body diagram down at that contact. If the contact is like that, the force has to be perpendicular. And then if you want a free body diagram of body 2, so let me just isolate a chunk of the ground. Newton's third law says that force on the chunk has to be equal and opposite to the force the chunk applies to the body. This force is like that. The second joint in joint category 1 is a roller. Oh, before I do that, one thing I need to say about this is notice the value of F must be positive. Because look at that free body diagram. What would it say if that force, if you did a calculation and that force F came out to be negative 200? It would say that the ground is pulling down on the object instead of pushing up on it. And frictionless contact can't pull. All it can do is push. So if you ever set up a problem like this and get a negative value, it either means the thing that's being designed isn't going to work the way it's supposed to, or you made a mistake in your calculation.
It's just basically normal force.
That's a normal force, yes. That's right. Yeah, same with rollers. So this is drawn. Sometimes you see it with just like a single wheel type thing. Or sometimes you see it with the body having sort of connected to a little roller skate. But this works the same way as a frictionless contact. So a free body diagram of body 1 looks just like it did in the last example. If that's the surface, the force is perpendicular to it. And Newton's third law says if you isolate the other body, it has to be an equal and opposite force. No, we won't do that. You could, but there aren't really any cases where you're ever asked for that. Um, I mean, you could definitely imagine cases where you would want to know what's going on inside the roller, but none of the problems you're going to see in this class ask for that. So you can just treat it exactly the same as a frictionless contact. And there is one more. So notice on this one too, um, that the value of F has to be positive. Because again, all the ground can do is push on those wheels. It can't pull down on them. And the third joint in this category is a pin in slot joint. So let me show you what that looks like. Okay, so this looks like you have one body there with a pin through it, and it connects to a second body with that pin sliding in the slot. I'll call this body 1, this body 2. A free body diagram of body 1. If the slot is oriented like this, then the force has to be perpendicular to that slot. And in this case, it doesn't matter whether you're drawing that arrow toward the chosen body or away from it. That slot can prevent motion in either direction. So you choose. But if this is the force applied to one body, the force applied to the other body has to be equal and opposite. For this one, notice that the value of F can be positive or negative. Okay, those are the 3 least restrictive joints. Now we're going on to joint category 2. The first one of these is contact with friction. Sorry. Let me say something about this one. Here's what joint category 2 has in common. These introduce 2 variables Newton's laws by applying a force vector with an unknown direction. Okay, so the first one is the one that we've already seen in this class, friction contact. In a problem, you would see that, it would look just the same as frictionless contact. You'd just be told that there's friction. So if this is body 1 and this is body 2, a free body diagram of body 1 looks like this. I was about to draw the surface, but you don't even need that because we don't know the direction of this force. So we'll just draw it as two unknown components and call this the force on body 1 by body 2. And then a free body diagram of body 2. Newton's third law says it has to be equal and opposite. So you can write this as the force on body 2 by body 1. Newton's third law says that's negative F12. And then the second type is a pin joint or a hinge. And so let me show you what that looks like. Okay, so pin joint. It's like this. One body there, one body there. So let's call that body 1 and that body 2. And a free body diagram of 1 looks like this. The force on 1 by 2. And a free body diagram of body 2 looks like this. Force on 2 by 1, which is the same thing as negative F12 by Newton's third law. That's all for that joint category that introduces two variables where there's an unknown force. How many more categories are there going to be? We've had a category that applies one force. We've had a category that applies two force components. Are there going to be like 40 more categories or no more categories, or how do you know? There's only one more because there's only one degree of freedom left to deal with. That's exactly right. So all that we're going to have for the last category is a joint that doesn't allow any translation and also doesn't allow any rotation. It's just like a weld joint or a joint. Two things that are just solidly, rigidly attached together. So joint category 3 is the most exclusive. It only has one member. So it introduces three variables. And it does that by applying full force vector and a couple. And there's only one of these. It's called a fixed joint or a weld joint. It's drawn either like this, or sometimes people draw it with sort of a dovetail like that. If this is body 1 and this is body 2, and a body diagram of 1 has the force on 1 by 2 and a couple on 1 by 2. And a free body diagram of member 2 has a force vector F on 2 by 1, that's equal to negative F12, and a couple M21, which is equal to negative M12. Any questions about that?
Is there a situation where there is just a couple, but it can slide in and out without rotating?
No, not that I can think of. All right, let's do one quick example. So let's say we have a bar connected to the wall by a pin joint, and touching a roller at its midpoint. And a downward force of 1,000 newtons here. And let's say the mass of this bar is 50 kilograms. Let's say that's half a meter, and that's half a meter. We want to know what are the reactions at those two joints. So I'll do a free body diagram of the bar. Kind of force is applied by the pin joint. That's one of those ones where we don't know the direction of the force, so I'm going to write that as, I'll just write that as R. It's an unknown force vector. And then at the roller, that force is applied perpendicular to whatever it's rolling along, the surface. So that's a force like that. I guess I'll call this one RA. I'll call this one the scalar RB. And then there's the weight of the bar, which is 50 times 9.81, 490.5. And then a downward force of 1,000 newtons. And it usually simplifies the math a little bit if you choose your about point to be where you have the most unknown forces. So I'm going to put the about point here. Okay, so For the force RA, what's the row vector? 0, yep, exactly. The force vector is RAX, RAY, 0. And there's no moment because there's no row vector. Next, the weight force. I'm going to just go through this pretty quickly. The row vector is positive 1, 0, 0. The force is 0, negative 490.5, 0. And the moment is 0, 0, negative 490.5. And the force RB, that also has a row vector of 1, 0, 0. The force is 0, RB, 0. And so the moment is 0, 0, positive RB. And then continue this down here. The force vector 1000. Going down, the row vector is, oh, I did the geometry wrong here. Let's just change the problem. You can't do this, just me. Don't do this on tests. Okay, so then the row vector is 2, 0, 0. The force vector is 0, negative 1000, 0. The cross product is 0, 0, negative 2000. And now I think I'll just stop there. But to do, for Newton's law, Newton's second law, you just take all these, add them together, set them equal to 0. And for the moment equation, you add all those up, set them equal to 0. You'll have 3 equations for 3 unknowns, and you can solve it. Okay, that's all.